Welcome back, guys. So we're going to continue chapter one, covering the topics in chapter one. So we already covered those topics. So we're going to focus mainly right now on the sign and unsigned integers and how to subtract, because as you might know, Intel computers, they do not have subtractors. So they have to come every time you see this part, like 4 minus 5, or subtracting 4 from 5. I read it in a very weird way. I read it actually in the Intel way or in the computer way. So if you subtract 4 from 5, there is actually no subtractor. So we need to convert this into 4 plus minus 5 plus minus 4. Okay, because we need to convert the subtractor into an addition. Okay, sorry, the subtractions into an addition. So subtractor is going to be replaced by an adder. And that decision was made for a lot of reasons, and one of which is they need to save space. So if we can do, it's a microprocessor. It's the space is really limited, and they need to save each and every inch in that part. So if they can do subtraction with addition, that space is going to be maybe used for some other things. Okay, so we're going to focus on this, and we're going to start with looking at the signed integers, because now we know the unsigned. Because in the unsigned, we don't have a problem. The only problem we have with the unsigned when we say subtraction, because when we say subtraction, though 4 is a positive number, it is going to be considered as unsigned, because this is going to be plus minus 4. So this is now going to move into the unsigned. So every time you see subtraction, that means you are moving the unsigned to the signed. That is how Intel microprocessor works. Okay, and we already looked at the byte, and we already learned that the most significant bit is the bit used that's going to tell us about the sign if we are dealing with the signed integers. If we're dealing with the unsigned integer, this bit means nothing. It's part of the number. But keep in mind now, if these bits, like the bit right here, is being used for the sign, then we no longer have 8 bits. We have 1, 2, 3, 4, 5, 6, 7 bits, right? So 2 to the power 7, guys, is going to be what? 128. Okay, so in terms of range, now we have positive range and negative range. So if you give me a byte, the range is going to be from 0, positive range, to 127. So these are 128 patterns or combinations. Okay, for the negative range, we're going to have, because I said it in the beginning, if you remember, we don't have a negative 0, so we're going to start from 1. So that is the positive range. We're going to start from 1 to the 128. Okay, why 128 and here 127? Because we don't have a 0 in here. There is no negative or positive 0. There's just 0. Okay, so this is what the range is going to be. All right, so be very careful when you deal with numbers in computers. Okay, because numbers means different things. Okay, as long as you know whether they are signed or unsigned. If you don't know this fact, then you are completely in a dilemma. Okay, so this is in terms of decimal, and this is in terms of binary. In hexadecimal, if you see this number 8D, that shows you that this number is negative, because 8 is greater than what? 7. So this is similar to looking at the binary number most significant bit. If it's 1, then it's negative. If it's 0, then it's positive. If you look at a hexadecimal number, and the number is the number in the leftmost, the digit in the leftmost is greater than 7, then this is actually a negative number. Do you see what I'm talking about? If you want to look at 8 in binary 0001, so the most significant bit is what? Is 1. So that is actually a negative number. Okay, if it's 7, this is 7, right? If we're going to say 72, this is 7, right, guys? And this is 2. 2 is going to be 0010, right? So I know the most significant bit is 0, so I know this number is what? Positive. So instead of converting it into a binary, if it's a hexadecimal, we're just going to look at the digit in the most left part. If it's greater than 7, 8 or more, 8 to F, then the number is negative if it's a signed number. These are very little things, but they're very critical. They're going to make you either answer the question the right way or the wrong way. Okay, so keep that in mind. That's what I was talking about. If you are given an 8-bit, the least number that you're going to have is negative 128. The maximum is going to 127. That's what I showed you in the previous slide. So it's going to be 0 to 127. And then the other range is going to be negative 1 to negative 128. Okay, so in this slide here, they gave you the entire range. So this is 2 to the power 7. Why 2 to the power 7? Because we know 1 bit is being taken for the sign. All right, and this is going to also affect the range for when it's 16-bit and so on and so forth. Okay, so this is going to be very important. So keep that in mind. Okay, so now we are dealing with the sign. Okay, so and we are handling the subtraction in general. Okay, so let's say we are subtracting 2 from 5. So in order to do this, as I said, we need a 2's complement system. So please forget whatever you know about the 2's complement system before this class. I want you just to follow what I have in here, because what I have in those slides is actually what is provided by Intel manual book. So I'm just following that part, all right? So you already know the motivation. We need it because we don't have what? We don't have a subtractor. We have to convert subtraction into an addition. Okay, and I already showed you the example, right? So for this example, we're gonna say 5 plus negative 2. Okay, so now the problem is how to represent 5 in binary. That is no brainer, right, guys? This is 5. We are dealing with 8-bit. Do not write something that's 4 or 5. You have to write everything in what? In terms of byte, the least. Why is that? Let me show you here. Because this is the storage provided by Intel. We go by byte or by word or by D word or quad word or double word. So if you are using a byte, you have to use 8 bits. Keep that in mind, please. So if in the exam, if you're just gonna say 0, 1, 0, 1, 1, you said I don't need the rest, that's okay. You are wrong, even if your answer is correct. So you have to show that, okay, this is 4 and this is 0, 0. So you have to show everything in terms of byte. That is something that it is very important to keep in mind from now onward. So we're going to say 5 plus what to write in here. This is going to be 2. So we don't know what negative 2 is, but we know what 2 is, right? So if we know 2, this is straightforward. This is 2, right, guys? You with me? So you have to write, as I said, keep in mind, you have to write a byte. So if this is 2, we are looking for what? We are trying to figure out negative 2. So that's the 2's complement. So first we're going to flip. It's going to be 1, 0, 1, 1, 1, 1, 1, 1. So that's the flipping. Okay? And then we're going to add 1. When we add 1, many of my students, they will add it to this part. So cross this one off. You're going to add it here. 1 plus 1 is 0 and a 1, right? This is going to be 1. And if I were you, I will put zeros in here because they're not going to change anything. So this is going to be 1, 1 and a 0. Sorry, 1, 1, 1, 1, 1, 1. Always count, guys, because missing a digit might cause you a problem. So 1, 2, 3, 4, 1, 2, 3, 4. So I know that this is a 2. Negative 2, I'm sorry. So we're going to have here 0, 1, 1, 1, 1, 1, 1, 1. Okay? So let's see what this is because now I know the result is going to be what here? If I subtract 2 from 5, the result is going to be positive 3 because we are dealing with the sign, right? So expecting the result to be 3. So you should get a 3 in here. If it's not, then there is something wrong, okay? So let's look at it right here. So 1 plus 0 is going to be 1, and this is going to be 1. 1 plus 1, 0 and a 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 1. 1 plus 1, 0, and we have carry 1. So the result is what right here? Remember, it's going to be, the result is, it is now 1, 1, 0, 0, 0, 0, 0, 0. Remember that, guys? So the result is positive, right? Because the most significant bit is 0. And if we say 1, 2, 4, 8, right? If we're going to continue, this is 1 plus 2, 3. So the result is 3. So I can do the verification. Then my work, I mean, everything works fine for me. The only thing that is not clear right now, why I have a carry? Because we usually have carry flag. Sometimes we call it overflow. This is for unsigned, and this is for the sign, okay? So here we have an overflow since we are dealing with the sign, right? But why do I have an overflow? My result is correct because overflow is either going to tell you you are exceeding the range or your result is not correct. I'll explain that later, but now we have an overflow. Okay? So you're gonna have an overflow, but that's what the 2's complement is. Okay, so don't worry about the steps and everything. The upcoming slides explains everything in details. Okay, is it kind of clear? Okay. So this is what I was talking about right now in here, inverse and the steps. You're gonna find them in here. I'm not gonna waste the time. And this is gonna be the algorithm. This is what you need to do. This is first, second, third, fourth, and fifth. So you'll find everything in steps, okay? I mean, in terms of steps right here. So you don't need to worry about the steps. So if you look at this example right here, if you look at this number, I can say 1, 2, 4, 8, right? So this seems to be what? This seems to be what? So we are subtracting what from what? So this seems to be 1, 2, 4, 8. So 4 plus 8 is going to be what? It's going to be 12. It seems it's 12 minus what? What is this number? 1, 2, right? So 1, 2 means what? 3. So we're subtracting 3 from 12, right? So this should give you what? Should gives you 9, right? But we know we don't have a subtractor, right? Correct, guys? So we know that this binary is going to stay right away 12 right here. The only problem we have is this number. Right? So this number is what? Is 3, but we need to convert it into what? 12 plus -3. So I have to convert this into a -3, but we have 3 in here, right? So what we're gonna do in here, we're gonna use the 2's complement, right, guys? So first we're gonna flip 0, 0, 1, 1, 1, 1, 1, 1, and then we're gonna add 1. So 0 to 1 is gonna be 1, 0, and everything else is gonna be what, guys? Is gonna be 1s. So isn't that what we have in here? Yes. So that's what it is. So you flip this. Okay, so that's what you did. And then now you add them. 0 plus 1, 1, 0 plus 0, 0, and then so on and so forth. Okay? So this is going to be 1, 1 plus 1, 0 and a 1, 1 plus 1 plus 1, 1 and a 1. Okay, 1 plus 1, 0 and a 1, 1 plus 1, 0 and a 1. 1 plus 1, 0 and a 1, 1 plus 1, 0, and we have a carry. Again, why we have this carry? But let's look at this part, 1, 2, 4, 8. So 8 plus 1 is going to be what? 9. So our result is correct. We are expecting positive 9, and this number is positive because the most significant bit is 1. So you might wonder where this one is going to go, right? It's the same question that we should ask if you go back right here, where this one should go, right? Okay? So this is what, if you remember in the big picture, when we talk about the E flag, so we have the E flag. So we have a flag that has 32-bit, 32-bit. We call this flag E flag. And one of these bits, okay, 2 of these bits actually, this is gonna be the carry flag, and this is gonna be the overflow flag. So this is for the unsigned, this is for the signed. So this one is gonna go to where? Carry or overflow? We are dealing with the sign, right? So this bit is gonna be set into 1. But when we have a flag, it means that there is something wrong, but there is nothing wrong in here, right, guys? But why we have a 1? I will let you think about it. We're gonna talk about it next week, but I want you to think about it. If my result is correct, everything is fine, why am I having a carry flag? That is very weird, okay? And there is a very special situation when the result is really hard to verify. So if we say 2 minus 4, right? So this is going to be what? 2 plus what, guys? 2 plus minus 4, because we don't have subtractors, right? So remember, the result is expected to be negative. If the result is expected to be negative, it's not going to be as easy as what we saw right here. We can read it 9, 1, 2, 8 plus 1 is going to be 9. We can verify it right away. That is not the case if the result is going to be negative. Okay? If the result is negative, then we don't know. It's just a negative number, but we don't know what that negative number represents. So we have to do reverse engineering the number again in order to get the final result. Okay, so let me show you what I'm talking about. You can look at this in more details, but I will try to write them right here. So if I have 2, this is my 2, right, guys? 0, 0, 0. I have to always make sure that 1, 2, 3, 4, 1, 2, 3, 4. Okay, guys, you with me? I know that this is 2, and then I have to add to it what? -4, right? So I have to treat the -4. So first, I know what 4 is. You with me, guys? So first, if you follow the algorithm I have in the slides before the previous one, so first I get the 4, and then I flip, right, guys? I'm gonna flip this one. And then I'm gonna add a 1, right? So I'm gonna add 1 to the flipped one right here. 1 and a 1, 0 and a 1, 1 and a 1, 0 and a 1. So this is 1. And then just imagine, as I said, always have zeros in here. They're gonna keep things in place. There's gonna be 1, 1, 1, 1, 1. So this is 1, 2, 3, 4, 1, 2, 3, 4, okay? So this is what I wanna add. So this is my -4 now. You with me, guys? Okay. Okay, so when I add this is my -4, right? So that's the representation because the most significant bit is 1, so that's a -4. But let's look at this. So 0 plus 0. So it's going to be 0. 1 plus 0 is going to be 1. 0 plus 1 is going to be 1. So these are all going to be 1s, right, guys? 1, 2, 3, 4. 1, 2, 3, 4. You with me? So I know that the most significant bit is 1. So this is what? This is a -4. But if you said 1, 2, 4, 8, 16, 32, 64, and 128, this is not a -4. It's not a -4. You agree? You have to add this one up, and it's going to give you a completely different number. Do not use this system if the number is negative. Do not look at it in this way right away. So if this is the result and you are confident, you can keep it that way. You are not required to flip anything. But if you want to verify, do not use this to verify. Use this system. So we're going to flip this again. 2's complemented it again. It's going to be 1, 0, 0, 0, 0, 0, 0, 0. We flipped everything, right? And then we add 1, right? So 1 plus 1 is going to be what? 0 and 1. And this is going to be my 1, right, guys? So when I subtract this from this, right? So I'm expecting the result to be what? To be -2, right, guys? Isn't this 2? Yeah, so I know that this is a negative number, so I know the result is -2. So I know my result is correct. You don't have to do this, just do it if you want to verify, okay? If the number is positive, if this is 0, just use 1, 2, 4, 8 and add the active bits all together, and then you're going to get the decimal number, and that's going to tell you whether your result is correct or not. So the example is being explained right here in more details, so you can look at the details right there. Okay, guys? Is that clear? So this is what I'm talking about with the sign. So this is a little bit confusing. So if I look at the hexadecimal like numbers, right? So if you look at the end sign, this is 0 to 15, because this most significant bit means nothing, okay? Just means part of the number. It's not the sign. But if it is a sign number, this is no longer 8, this is -8. This is no longer 9, this is -7. Do you see the image now is completely different? 10 becomes -6. So if I give you this number and then I say 0, 1, 0, 1, and I ask you what this number is, you should not answer, right? You should tell me, do you mean sign or unsigned? I say sign, then you're going to say, okay, this is a negative number, but I don't know what it is. How do I know what this number is in positive number since it's a sign number? So it's very simple. I will just gonna do it right here. So I'm gonna say 0, 1, 0, 1, right? And then I'm gonna flip this 1, 0, 1, 0, and then I'm gonna add 1, 1 and a 1, 0 and a 1. So this is 1, 1, 0. So this is 6, right? 1, 2, 4, 8. So 4 plus 2 is 6. So I know I will tell you this is -6. Okay? The same thing, you see, that's what during the office hours, I was telling one of your classmates that there are some crazy things. This is one of them. The same pattern now, if you consider it ensign, this is a 10, right away 10 right here. You see it? So it depends on the most significant bit. If the most significant bit is considered as the sign, then it's -6. If it is ensign, then it's 10. So the computer sees it 1, 0, 1, 0. It doesn't matter. So who defines sign and unsign? It's us. So in Java, when you say integer A, have you ever thought about what integer is? Integer is sign or unsigned in Java. It is sign. Okay, if you say unsigned, you're wrong. It is sign. Okay, so you have to be careful. You define this. Okay, so we have to tell or have to convince the hardware that this number could be -6 or this number could be what? 10. Isn't that crazy? It depends on whether you mean sign or unsigned. Okay, so these are all things that we make. Okay, as a human, we made them up to help us understand a few things. If you drive in the highway, don't you guys see the white line in the middle? Is this a physical thing? Definitely not. Is it logical? Yes. So it's going to help us switching sides, right? So we made it to organize the traffic, but physically it has no meaning. It's the same thing. Sign and unsigned, they mean nothing to the computer. They mean something for us. So keep in mind, when we had the overflow, this is part of the clue, because the computer doesn't care. Hardware-wise, it's just 1010, that's it. You interpret it as a 10 or you interpret it as a -6, that's up to you. Do you mean unsigned or signed? I will keep talking or bringing this point up every time possible, so just to get you very close to the hardware. Okay, guys? All right, so I would say try to practice 2's complement and try to look at those examples as much as possible. If I were you, I would do this one, 2 minus 7 or 3 minus 9, okay? And try to do them in binary right away. So you know the result right here is gonna be -5, and you know the result right here is gonna be -6. So you know this part right here is gonna be 2 plus -7, and for this part here is gonna be 3 plus, because we don't have a subtractor, -9. So now you need to get the 2 right here. This is your 2, right? Remember when I said binaries and converting from decimal to binary and vice versa, and hexadecimal to binary and decimal? Do you feel like how important it is? It is a little thing, but you need to master it right now, okay? So if that is the case, then now I have to think about 7. So I know this is 7, right, guys? But I'm after -7, so I have to flip, right, guys? And then I have to add 1. So this is gonna be 1, 0, 0, 1, right? And this is gonna be 1, 1, 1, 1. So I put this right here, 1, 0, 0, 1, and then 1, 1, 1, 1, right? And add them up, and you should get what? For this part, you should get -5, but you're not gonna get -5, right? I mean, at least you cannot read it because it's gonna be hard. The result should be negative. So 0 and a 1 is gonna be 1, 1 and a 0, 1. This is 0, this is 1, 1, 1, 1, 1, right? So this is a negative number. But in my mind, I know this should be -5, but I don't know. If you wanna verify, you need to flip it up. So if you wanna flip this one, this is 0, 0, 1, 0, right, guys? 0. 0, 0, 0, and then we're gonna add 1 to this, right? If we add 1 to this, let me put the result right here. 0 plus 1 is gonna be 0, and this is gonna be 0, right? And then this is gonna be 1. Sorry, 0 plus 1 is gonna be 1, I'm sorry. 0 plus 1 is gonna be 1, and then these are all zeros, right, guys? You with me? So 0 plus 0, 0, 1 plus 0, 1, 0 plus 0, 0. So these are all gonna be what? Zeros. So this is 1, 2, 4. So 4 plus 1 is what? 5. So I know since this is a negative number, I know this is -5. Okay, so do it with this number and come up with your own numbers, okay? If the result is the other way around, do it in this way, -2. So this is gonna be 5, and what you need to handle right now is 7 plus -2. So try to play with that. All right, guys? Okay, so now we're done with the integers. Of course we are not, this is just the beginning. We're gonna do integer sign and unsigned forever, and we're gonna do it when we write the code, right? We're gonna see it using the assembly code, but I'm just showing you the foundation, the theoretical part of it, okay? So if that is the case, now we're gonna move into how to represent, because the whole idea is representing data, right, using binary system. Now how to represent character, right? So how to store a character. So we know that back in the days, everyone has its own way to store characters. They have their own system until the time comes, when the time comes and they said, no, we need a standard way. And then they came up with the ASCII. Okay, so if you are using the ASCII, which is very, very common nowadays, the Unicode, ANSI, and extended ASCII, these are all comes out after what? After the ASCII. Okay, and then we have another way. This is the character sys. This is what we call null terminator. So the null terminator is that you have a \0 at the end of the string. Because the good thing about the string, guys, or the bad thing, if you want to look at it that way, you don't know the range. You don't know the end of the string. If it's an integer number, you know it. You have from 0 to 255 if it is unsigned. If you go to 256, the computer knows something is wrong. But with the string, that's not the case. So you have to tell how to read, how to store, and how to write a string, because we don't know the end. So one way to do it, or one way to identify the end, is to write \0. So if you have, let's say 1001, 0001, if this represents small letter a, then we have at the end, when we store it, 1, 0, 0, 1, right? And then we're gonna have 0, 0, 0, 1. So we know that this is for the null terminator, okay? So I'll talk about that in more detail. So this is how, I know that you already know this, but I'm just gonna show you that right here. So this is how you store capital A. So if you look at the capital A is gonna be 65, right? In hexadecimal. And we know 65, this is what 65, right? This is 5, and this is 6. So this is how you store a capital A. Okay, small a right here is going to be 97, right? So this is going to be 6, and this is going to be 5. This one right here is going to be what? 97, right? So this is 9 and 7. I know every hexadecimal can be represented by 4 digits, right? So this is 9. Okay, 1, 2, 4, 8. 8 plus 1 is 9. And 7, it's going to be 7 is going to be 1, 2, 4, right? So 1 plus 2, 3. 3 plus 4 is going to be what? It's going to be 7, right? So this is going to be what? This is going to be small a. Do you see the difference right here? They're completely two different things. So just look at the ASCII and try to play with the binaries right there. Okay, so this is the way we store the ASCII. I'm just reminding you. So I would just share with you an example right here. So this is a binary number. If you look at it right here, this is small letter a. Okay, so if I want to read this in decimal, then this is 1, 2, 4, 8, 16. This is 32, and this is 64. So I have 64 plus 32 plus 1, right? So 4 plus 2, 6 plus 1, 7, and 6 plus 3 is going to be what? 9. So I'm having what? 97. So that's 97. If I want to do this in hexadecimal, I divide by 4. So this is going to be 1, and this is 1, 2, 4, 8. So 2 plus 4 is going to be 6. So it's going to be 61. Okay, so you're going to store it in this way. Okay, either you're going to store it in binary in this way, or you're going to read it as in decimal or in hexadecimal. It doesn't matter. Okay, so this part I used to spend like at least a whole lecture for it, but I don't have time. I have to skip it. As I promised, I will try to keep the, I will add the slides that I removed from the original one, just in case if you want to look at it. So the whole idea is you need to learn how to build an adder and a multiplexer just using the logical gate. So these things you're going to learn in more details when you're going to go to the computer architecture. They're going to show you how to build multiplexer, adders, memory, microprocessor out of this gates. Okay? So with that, now, as I said, you're going to go and do the Boolean. So with that, we already covered the main components of the chapter 1. So as I said, I hope you guys are around this part. Usually that's the case. I think after the first week, I'm going to have few people around here, okay? So you're going to be always wondering, and you are ready to put the effort, and then you're going to move here and move there, hopefully at the end. Okay, so this is what it is right now. So I will upload the slides and the chapter, the slides for, the video and the slides for the chapter 1, they are already there. Okay, so thank you very much, guys, and see you next week.